Thank you very much. So now yeah, so please so Akihiro will continue.
Yeah. So this is the second lecture. So now I'm to introduce the concept called association scheme that will generalize the property that it commutes those matrices which are obtained from two orbits. They commute with the permutation matrices of the action. So let me review what we did in the previous lecture. In the previous lecture, I proved, that was the final proposition, that if I take a action and the two orbits R and form an adjacency matrix AR, then it commutes with the permutation matrix PG. Well, if you think of the proof that I have shown you, then it actually completely characterizes the two orbits. That is, in some sense, the converse is also true. So the adjacency matrices commutes with their permutation matrices, but on the other hand, conversely, anything that commutes with the permutation matrices are essentially adjacency matrices because they are just the linear combination of adjacency matrices. So to make it more precise, I consider the set of all permutation, not permutation matrices, but all matrices which commute with the all permutation matrices of the action. So this is called the centralizer algebra of G. The word centralize means commute. So the commute and centralize are synonyms in mathematics. And what I said is that this algebra, well, it is called algebra because it is closed under addition and multiplication also. So this is a sub-algebra of the full matrix algebra consisting of those matrices which commute with permutation matrices. And it turns out this has a basis consisting of adjacency matrices of two orbits. It means that every element of the centralizer algebra is a linear combination of this adjacency matrix. It's clear that the adjacency matrices are linearly independent because they have ones in different positions or disjoint positions. Well, the proof is quite obvious because of the property that the entries of the adjacency matrices are invariant under G, and that characterizes adjacency matrices. Because what it means for X to be in the centralizer, it means the entries are invariant under the G action. But those matrices, 0, 1 matrices which has this property are just precisely the adjacency algebra. So the entries of X are constant on the support of the adjacency matrices, so it's a linear combination of adjacency matrices. Now, for convenience, I will give numbers to the adjacency matrices or two orbits. So let us suppose there are small r, two orbits of the action. So let us call them R1 to R sub R, and then they form the basis of the centralizer algebra. And because it is closed under multiplication, you can find some scalars P, I, J, K. In fact, they are integers because we are dealing with only 0, 1 matrices. And so you can express this product in terms of linear combination of the basis again, because they also also, the product is also an element of the centralized algebra. There are two more, in fact, three more properties. But I gave numbers, but I don't refer in the later slides, so don't worry, you don't have to memorize them. The second property is that it is closed under transposition. That is, if you transpose the adjacency matrix of some relation, then it becomes adjacency matrix of some other relation. Well, this is because if you have an orbit and you exchange the first and second coordinate, and you get another two orbits. And the third relation condition is, sorry, I should have written A sub, not, later I will introduce this shorthand notation, but then it should be A of R. Yeah. So if you sum all the adjacency matrices, then it becomes all one matrix, because that's two orbits partition omega squared. And moreover, the action is transitive, so if you consider those elements in the diagonal, that is the alpha in the omega square, then that restricted action is transitive. So the action is transitive, then there is a single two orbits which whose adjacency matrix is just identity matrix. So in that case, well, we might as well assign number one for that relation. So these four properties are used to define association scheme. So we start with a permutation group. In fact, we started with a transitive permutation group and define those canonical bases indexed by the two orbits. And these are the principal properties of those bases. So these properties are used to axiomatize what is now called the association scheme. So now we forget about the group, action, but we only consider subsets of omega square. Rather, it will be a partition, but we don't consider the group, but we just consider those relations which have exactly the same property as I mentioned in the previous slide. There are four properties. So if you consider the adjacency matrices, then the product is again a linear combination of those adjacency matrices, and it is closed under transpose. And also it forms a partition so that if you sum all of them, then it becomes a one matrix, and diagonal is also a single relation. So such a family of relations is called the association scheme. So of course, because those properties are derived from transitive action, so the set of two orbits of the transitive action is an association scheme. Now, I will use a shorthand notation, the 1 sub omega, to denote the diagonal relation, and also the transpose of a relation is just the switching the first and second coordinate. So if R is a relation that is a subset of omega squared, then R transpose is another subset. It could be the same or could be different. But in terms of matrix, this identity matrix corresponds to this special diagonal relation, and transpose just corresponds to just the transposition of the matrix. And another property, which is, I already mentioned, that it forms a partition. That is the sum of all adjacency matrices is equal to J. So these three are 3 out of 4 properties required in the definition of association scheme. So they are easy to describe combinatorially. So except this very first one that is closed under multiplication, the other three properties can be expressed without using matrices. So first it's closed under transposition. Now because I have defined transposition of relation, so I can forget about the matrices. It's closed, the set of relations is closed under transposition. And the partition and the diagonal. So the only thing which needs to be understood combinatorially is this closure under multiplication. So what is this constant Pijk? So Pijk, if you look at this matrix equation, Pijk is one of the entry of this matrix because the ARK, those adjacency matrices have disjoint support. So Pijk is in fact one of the entries of this matrix. So if I take that position where this Pijk appears, that is precisely those positions which are indexed by the kth relation. But then on the other hand, the left-hand side is the product of two matrices, so I can compute the alpha beta entry of the left-hand side, which is of this form, but this is the 0, 1 matrix, so instead of computing the product and sum, you can just count the number of occurrence of ones. This is 1 if and only if the both of these two factors are 1, that is precisely alpha gamma is in the ith relation and gamma beta belongs to the jth relation. So this is understood very nicely if you draw a picture of a triangle. So Pijk counts the number of elements gamma which can satisfy this property. So fixed alpha beta in the kth relation, and gamma is required to satisfy two conditions. Alpha gamma is in the ith relation, and gamma beta is in the jth relation. Because the relations could be directed, it's important to understand, to know the direction. These relations may not be symmetric. So this is called the intersection number. Or you could say that it is an intersection number of a transaction. So the adjacency algebra is the algebra formed by these adjacency matrices of associations. This is closed under multiplication, so it is an algebra because of the definition of associations here. It is also closed under transpose. That's also part of the axiom. And it is also closed under the entry-wise product. The reason is that it has a basis consisting of 0, 1 matrices. It is enough to note that it is the set of bases is closed under, well, not the basis, but this entry-wise product of two basis elements is again in this algebra. But this is quite obvious because if you take an entry-wise product of 0, 1 matrices, it then is either itself or 0 because it's a relation, then those relations form a partition. So now let's consider the particular example, the right regular representation. So again, we are back to the permutation groups. So we take a finite group G and consider the right regular representation. So we have seen that the two orbits of the right regular representation have a very particular form. It looks almost same as the permutation matrices, except that the group element acts from the left. So I also mentioned that they are also called the left regular multiplication. So in short, the centralizer of the right regular multiplication, right regular representations are just a left regular representation.
Don't you need
Yeah.
the inverse of beta at the very end of the line?
Oh, maybe beta at the end? No, I don't here.
Here.
No, I don't think so.
Because you say alpha beta minus 1 equal to g2 minus 1, and then you write the delta function. Sorry.
Comma should be replaced or deleted just.
Yeah, comma should be.
Comma should be deleted.
So comma should be moved to the left.
This comma should be.
Maybe not.
No?
Yes?
I was thinking the last alpha beta should be subscript inverse. Subscript.
Alphabet, I mean, the alphabet are group elements, so you can multiply it.
You have subscript on the left hand side.
But there is no comma then. It is there.
No. It's correct.
Just notation.
Oh, okay.
Yeah.
Okay.
Well, this might appear also in the previous lecture. But,
Yeah.
Okay.
I think it is correct.
It's okay.
Thank you. Sorry.
I mean, this is Kronecker delta. You can move because it's a two-variable function, and you can move that other group element to the other side because it's only constant equality of two variables. So the centralizer of the right regular representations are those matrices which is of this form. Because if you take R and pick element G1, G2 from this R, and then we may decide to call this particular element G. And then this matrix has alpha beta entry, the Kronecker delta G inverse of G inverse alpha comma beta. So this is same as this with if we denote this particular element by G. So this is nothing but the left regular representation. So left regular representation commutes with the right regular representation. Of course, if you think of just not by in terms of matrices, but in terms of permutation representation, it's clear that left regular representation commutes with right regular representation because it's just nothing but the associativity. And left regular representation is also, it is also legitimate to call it representation because it's a homomorphism. So for this matrix also, it is the assignment of this matrix to G is a homomorphism. So, but then what is this centralizer algebra? Centralizer algebra is this, in this case, f of the relations, the adjacency algebra, but this adjacency algebra has a basis consisting of this regular representation, and so it is also a group algebra. Well, it's not exactly the same as the algebra of right regular representation because the algebra of right regular representation are not commutative, but they commute with the centralizer. So you have an isomorphic algebra which commute each other but not the same. So they both live in the full matrix algebra of size order G. Now this example is important in the problem solving session because I leave the student to fill out the details of the slides, the expressions stated in these slides. So the Johnson scheme, this is a particular example of association scheme. Yeah, in fact, this is with the, well, this is easy to think of, but it turns out it is very important as we attended or some of us attended conference last month in Pilsen, Czech Republic, and this family of association scheme is precisely has a very important role, most important role in the graph isomorphism problem. It constitutes the main obstacle. But we don't talk about this problem in the lecture, but so we only concern with the description of the Johnson scheme. So Johnson scheme consists of omega, which is just a set of all two-element sets of n-element set. So G itself is a symmetric group, but it's not the canonical action on n point, but it acts naturally on the set of all two-element sets. So Sn is a shorthand notation for symmetric group on the set of n elements consisting of numbers from 1 to n. So G acts naturally on omega, and it is easy to see because its symmetric group can move every two-element set to another two-element set in completely coherent way, so you can find two orbits easily. One is, of course, diagonal because it's transit, and the other two, you can think of these two orbits as intersecting, because whenever you have two sets of size 2 intersecting at one point, and another pair of two sets intersecting at 3, then you can find certainly a permutation which maps this pair to that pair, because you can just specify the image of these 3 points to that 3 points, and then the rest, there are n-3 points, completely arbitrary manner to another n-3 points, because we are in the symmetric group. You are free to choose image of any element as long as it is a bijection. So it's clear that these R1 forms two orbits, and R3, R2 is you just have now disjoint pair, so now you require 4 points instead of 3, but still the symmetric group acts transitively on this set R2, and R0, R1, R2 partitions the omega square, so you get complete two orbits. So I decided to use 0, 1, 2 as index instead of 1, 2, 3, because this is precisely the distance in the graph called the Johnson graph, whose set of edges is simply just R1. Now, there are formula to how you multiply those matrices. So I use the shorthand notation for A sub Ri. I simply write AI, and it will be the problem during the problem solving section to establish these formulas. If you square this adjacency matrix A1, you get some linear combination of these. This property will be explained in Misha Muzicuk's talk, because he will introduce strongly regular graph. I will not do this here. So once you learn about strongly regular graph, you will see the meaning of this equality. And if you elaborate a little bit more, you can find that A1 satisfies this cubic polynomial, and these 3 numbers are different, and then they are precisely the 3 distinct eigenvalues of the adjacent matrix A1. The first equation shows that you can solve this for A2. So A2 is a polynomial of the degree 2 in A1. So if you want to generate the algebra, then you don't need A2. the algebra is generated by A0, A1, A2, but the A0 is identity, so it's automatically in the algebra. A2 is a polynomial in A1, so you don't need A2, so it is generated by a single element, A1, so it is a quotient of a polynomial algebra divided by the minimal polynomial A1. In terms of the minimal polynomial is exactly what I have written here. So it's a cubic polynomial. So this algebra is a polynomial algebra divided by a cubic polynomial. So it's isomorphic to the C3. So this is the adjacency algebra, which is in fact commutative, and it's very simple structure like C3. Of course, in the previous slide, we encountered that the adjacency algebra, which turns out to be the same as the centralized algebra, for the right regular representation. The right regular representation, the centralized algebra, is a left regular representation, which is isomorphic to the group algebra. So it could be highly non-commutative. So we have adjacency algebra, which could be as easy as to understand as in the Johnson scheme, it's just 3 copies of fields, or it could be very complex as group algebra, it's highly non-commutative as group algebra. But our goal is not only to determine the abstract structure, like C3 or maybe the algebra, the direct sum of matrix algebra, not only to determine the structure as abstract algebra, but to find the numerical specification of the distinguished bases. Because in our algebra, there are 2 bases. One is, of course, the adjacency algebra, adjacency matrices. The other, which I will introduce, that the primitive idempotence. So, what are the primitive idempotence? For example, for the commutative case, like in the case of Johnson scheme, the algebra is isomorphic to the 3 copies of complex numbers, or you could do some other field, but I will only consider complex numbers from now on. But they exist. This means that there exists another distinct basis, because it is abstractly isomorphic to C3. So you may think of these three as just a plane, not a plane, but a space. So you have 3 coordinates. Those 3 coordinates, because it is isomorphic to C3 as an algebra, so they multiply coordinate-wise. So the unit vector play a special role in the multiplication, that the unit vector multiply each other like idempotence, and you have a different unit vector, the product becomes 0. That's the coordinate-wise multiplication of vectors. And so this C3 means that the algebra is exactly like the coordinate multiplication of vectors. So it means that there is a canonically defined basis corresponding to this coordinate unit vector. So we have 2 bases canonically attached to the commutative centralized algebra. So it means that the change of basis matrix is of importance, because we have 2 bases, both are canonically determined. So it makes sense to talk about how one can describe, how one can express the one basis by another basis. So it is called the change of basis matrix in standard linear algebra, and this will play a central role in the rest of my lectures. Now we come to the description of the problem-solving session tonight. I mentioned that there is a very interesting group, a Matthew group, discovered at the end of the 19th century. 18, 17, 17, something. Yeah, I'll have program sheet printed, so that it will be distributed to students attending the program session. So the two orbits of the Matthew group, M23, there is a group called M23 Matthew group, which is a subgroup of symmetric group on 23 letters. So because symmetric group acts on the Johnson scheme, or the set of all two-element subsets, so the Matthew subgroup also acts. But this Matthew group is large enough that it is also transitive on the two orbits of the Johnson scheme. If you take a very small group, then the orbit will decompose into smaller pieces, but the Matthew group has highly enough transitivity, which I will mention details in the problem solving section, that they have exactly the same two orbits as the symmetric groups, namely R0, R1, R2. So the centralized algebra are exactly the same, because the centralized algebra has this as a basis, and abstractly isomorphic to C3, so we have special eigenvalue basis. Now, as I mentioned at the end of the previous lecture, this Matthew group has another permutation representation of the same degree, 253. 253 is, by the way, the cardinality of this set. That is the 23 choose 2. That is 23 times 22 divided by 2, 23 times 11, which is 253. So that permutation representation it's called the blocks of the width system. This is usually denoted by W23 because it was width who proved the uniqueness of this width system, and the Matthew group acts as an automorphism group of this width system. Width system is a design. In fact, it is a four design. And I think the Misha Muzichuk will give the definition of the design in his lecture, so I will not give you details about the width system, but of course I will give you detail about the width system during the problem solving session. It turns out that this width system has precisely 253 blocks. It is same as 23 choose 2, but it's not. It turns out it's nothing to do with 23 choose 2. It's just the numbers are the same. So the Matthew group acts transitively on blocks, but it turns out also it has rank 3. That means that it has precisely 3 orbits. It acts transitively, so there is a diagonal orbits, but there are 2 other two orbits of this Matthew group acting on blocks of the width system. And then, if you have only 3 orbits, then from the general theory of association scheme, which I haven't mentioned yet, but you will see in the next lecture that it is necessarily commutative and isomorphic to 3 copies. So you can't distinguish these 2 actions if you just look at the abstract type of the centralizer algebra. They are both isomorphic abstractly to 3 copies of complex numbers. But they are, in fact, different in numerically. I will explain what it means numerically. That is, the change of the basis matrix is P and P prime, because it could be different. It turns out to be different. That these 2 change of basis matrix, they are canonically defined for each of the permutation representation, but they are completely different 3 by 3 matrix. So the goal of there are two goals in the problem solving session. Not tonight, but there are two sessions. So hopefully by the end of the second problem solving session, we hope to achieve two goals. One of the goals is to see that two matrices P and P prime are different. So these two permutation representation of degree 253 of the same group that have this isomorphic centralizer algebra, but that they have different numerical specification because these two matrices are different. The other goal of this problem solving session is, one is the first goal. The other goal is that these two permutation representations are equivalent as a representation. I have mentioned the equivalence of representation, the representation metric representation. Because permutation representation can be thought of a representing group by permutation matrices, then one can see if the vector space, if there is a vector space isomorphism compatible with the action of the permutation representation. Not the bijective mapping of two sets, omega and beta, but rather the vector space isomorphism. One vector space is indexed by omega, the other indexed by this block big. It turns out there is an isomorphism vector space which commutes with the representation. So we will see the reason why, hopefully by the end of the second problem session, that these two are in fact equivalent representation. This is not meant for experts, because for experts it's quite easy to verify. For example, one can use computer now, because M23 is not, well, we have all those finite simple groups in the database. And if you even don't have a computer, you can still look at the atlas of finite group and what kind of a representation the M23 has, and it's easy to find out which irreducible representation appear in this M23, and using computer it's easy to find these matrices. But I'm not asking students to use computer, but to just use definition and property of the matrix group to see if these two matrices are different. Also, I will explain how to prove these two representations are isomorphic without actually constructing isomorphism. That technique will be explained in my third and fourth lecture. So the student will know by the beginning of the problem session enough knowledge about those techniques. Okay, so sorry, it's a bit early, but that's all I have for the second lecture. Perhaps I guess Sasha Ivanov will comment on the history of this particular pair of inequivalent permutation representation. I learned this permutation representation from my advisor, Ichibanai. His comment was that some representation theorists, not in combinatorics, have misunderstanding that the permutation representation are just a special case of representation, and it's not worth studying individually, but that it's just within the framework of a representation theory. That is not true, because this particular example shows that the knowledge of general representation, the irreducible decomposition of this permutation representation, gives no information about how this numerical specification P and P prime. So the general representation deal with how to decompose given representation into irreducibles. So it's important for them to know how this permutation representation is a sum of irreducible, but that information is not enough to understand difference between these two permutation representation. So that was what I heard from H. Banai, but perhaps Shayanov has different his comment on this pair of representation. Okay, that's all.
Thank you very much. Thank you. Oh, thank you. I just might say that this is really interesting example because happened very rare that you have two representations of simple group of the same degree and the permutation of characters is the same. Just happens. That's the bad point. No, maybe it illustrates something then when you have an abstract representation given in terms of irreducibles, then there is possibly more than one way to choose a basis to turn it into permutational representation. But any more comments or questions, please? Or if not, so thank you very much.
Thank you very much.